Hi, this is K. Raju Yadav from Institute of Aeronautical Engineering, Autonomous College, AIML branch, applied to CSC. I'm recording now the Tech Talk video of Computer Organization and Architecture, and my topic is Reduced Instruction Set Processor, Risc. The meaning of this Risc is it is micro-architecture implementation of reduced instruction set processor is more complex and maintaining the clock per instruction CPI close to 1 is always challenging. The deviation of CPI from ideal value is due to several reasons such as branch, misprediction, memory, latency, pipeline hazards, etc. The proposed paper analysis the processor microarchitecture design and effect of ISA pipeline and microarchitecture design. The Risc ISA pipeline has 5 stages, namely, first one is fetch, and the second one is decode, and the third one is register, and the fourth one is execute, and fifth one is write back. Pipeline is organized in such a way that integer and floating point execution units are independent to enable concurrent execution of integer and FP computations. Related works to the Risc. Currently, few open sources, ISS, OpenRisc, Spark, RISC-V, etc. available for designing low power Risc processors targeted on AISC, ASIC, and FPGA. An implementation of Leon Spark processors at 28 nanometers has been evaluated with a low voltage standard cell and memories. An instruction set extension on OpenRisc ISS for digital signal processing is implemented and integrated to the base instruction set. In an ISA, design criteria has been proposed and synthesized of the processor instruction set from the high-level description of ISA has been reported. Our architecture is a 32-bit single-core 5-stage pipeline processor with single issue out of the order FPU and integer computations, and in order commit and retire. Proposed core has been synthesized on FPGA and 65 nanometer and 130 nanometer technology nodes. Low leakage and standard process for ASIC. The synthesis results have been compared with similar efforts on Risc. 5 is ISA compatible processors. RISC-V instruction set architecture. The characteristics of this ISA provides user and supervisor level instructions to enable support for software stack, including operating system, base. RISC-V ISA has fixed length 32-bit instructions that must be naturally aligned on 32-bit boundaries. RISC-V ISA supports both integer and floating operations. Floating point operations are compatible with IEEE 754-2008 standard. RISC-V is ISA defined as base integer ISA, which doesn't have any architecturally visible delay slot for branch operations and support optional variable length instructions encoding. Register file organization. In this register file organization, RISC-V supports both integer 32-bit 32 and floating point integers 32 and 64-bit for user and the supervisor level processor modes. For single precision floating points data types, the lower 32-bit of floating point register is valid. The register R0 is odd-wide to the 0. Instruction grouping. In this, there are several categories and opcodes and instructions related to the different categories. First one is the branch instruction, and the second one is load instruction, and the other one is the store instructions, ALU instructions, atomic operations, system instruction, special unconditional jump, synchronization. These are the categories, and the related to their opcodes are there, and the instructions are also there. In this table, depicts that the instruction grouping based on the opcode field and functionality, both single and double precision floating point operations are classified into FPU related instructions. Pipeline organization and microarchitecture of RISC-V instruction set processor. RISC-V instruction processor adopts typical micro architecture within order, fetch out of order, execution, and in order completion. Proposed architecture comprises of 5 pipeline stages, namely fetch, decode, register select, execute, and write back. These are the 5 pipeline stages. Top in the figure of this top level architecture of RISC processor: fetcher, decoder, register select, execute, and write back. Register select stage. In this fetch stage, first one is the fetch stage. Instruction is fetched from instruction memory from location indicated by program counter PC. It computes the current PC and predicts the next PC value. Fetch until has a 32-bit register to hold the current PC value. The 32-bit adder to calculate the next PC by adding 4 to the current PC. Next PC is predicted either as PC plus 4 or by using a sophisticated branch predicted scheme. branch prediction scheme consists of branch of a branch prediction BP unit. BTB unit outputs Boolean valid signal along with target PC address. BP units provides Boolean information which contains whether PC value is present or not. The multiplexer selects either PC plus 4 or predicted PC as next PC value based on valid and prediction signal. The PC and the next PC are given to the decoder stage for further processing. The next one is the decode stage. In this, the instruction decode receives the instruction from program memory with corresponding PC and predicts from fetch stage. And the flow diagram of instruction decoder based on the lower 7-bit opcode of instruction. Instructions are classified as per table. Subgroup information is decoded from 3-bit field. Address of resources, destination register are 5-bit field each, and their position is fixed irrespective of type of instructions. If an immediate type of instruction has occurred, the immediate data is signed, extended to 32-bit for further processing. The register select stage. RS stage accepts decoded information for instructions from decoder stage and select the operand from either integer or floating point register file. RS stage contains an integer 32 number of 32 bits wide and floating point register file. Register file is implemented as a random access memory which has a latency of 1 clock cycle with 3 read ports and 1 write port. The register file organized for Risc fifth processor. Register file unit accepts 3 sources addresses read address 1, read address 2, read address 3, and the control signal which specifies the access of register files. Output is 64-bit, which holds the data from either integer or floating point register, has 164 write part of write back. And the next one is the execution stage. Execution stage consists of 3 concurrent units for integer arithmetic and logic operations, operand memory address computations, and floating point computations. Integer execution performance arithmetic, example of addition, subtraction, multiplication, and division. And logical is a AND, OR, XOR, and shift operations. Also, integer arithmetic unit calculates the target addresses for unconditional or conditional jump and branch instructions. Integer execution until executes the system related to instruction such as SCAL, SD break, instruction for supervisor level access to the instruction. An efficient data for forwarding schemes is used to forward output of execution units to the input of execution units. Detailed microarchitecture for data forwarding scheme is explained in section 6th. Write back stage. Write back stage commits the instruction from the pipeline and updates the register file with results from execute units. WB reads the instruction from top of the schedule instruction, first in, first out, and based on the pipeline information, it reads either from integer or memory or floating point concurrent units. Microarchitecture of how microarchitecture design of out of order floating point unit. In this, there are several. The first one is a FPU request, and the second one is input decoder, and the other is the scheduled instruction if first in first out, functional units, output decoders, and FPU response. Design issues and options in Risc-V pipeline. In this, the design issues are data hazards, control hazards, grouping of instruction, decode level logic, register file accessing, and pipeline operands operations. Verification and analysis of the risk. Verification of code, implementation of FPGA, implementation of ASIC. And the conclusion is the a 5-stage pipeline 32-bit instruction set processor compatible with Risc-V ISA has been micro-architectured and analyzed the design issues options for pipeline stages. In terms of grouping of instructions, decoder logic, complexity, register file access, control flow instructions, processor includes a sophisticated branch prediction and advanced data hazard detection with data forwarding. Unit and I3 IEE 754 2000 compliant out of the order execute in order commit FPU. Both integer and floating points of pipeline are verified at test branch level. Course implemented on Selim Vertex and AICE library. Thank you.